Assalamu alaikum. My name is Dr. Yahya Hassan, ITC Department, Bowen University, Kuwait branch, and this is Chapter 2, Data Representation in Computer Systems of the course TM103. By the end of this lecture, the student can describe the numbering system, converting between the bases, learn three methods for representing signed numbers, and represent numbers using floating point representation. These are the topics that will be covered during this session: positional numbering system, convergence, signed integer representation, and the floating point representation. Let us start by the first topic, which is the positional numbering system. The general idea behind positional numbering system is that a numeric value is represented through increases power of a base, and this is often referred to as a weighted numbering system because of each position is weighted by a power of the base. Any numeric value is represented through increasing power of base. Set of valid numbers or numerals, digits, is equal in size to the base of that system. The least numeral is 0 and the highest one is the base minus 1. Adding 1 to the highest numeral gives 1, 0, which has different meaning based on the numbering system. In the decimal system, 1, 0 means 10, while in the octal system it means 8, and so on. So the most important bases in computer sciences are the decimal, or sometimes called the denary. It has a base of 10. The number of valid numbers is 10, which equal to the base. The set of valid numerals is 0, 1, 2, up to 9. So we have 10 numbers, 10 digits. Adding 1 to the highest numeral gives to 1, 0, which is 9 plus 1 equal 1, 0, which is 10 in decimal. We have the binary system. It has a base of 2. The number of valid numerals is 2, which equal to the base. These valid numerals are 0 and 1. Adding 1 to the highest 1, so 1 plus 1 equal 1, 0, which is equal to 2 in decimal, or 1, 0 in binary. Octal, the base is 8. The number of valid numerals is 8, which equal to the base. The set of valid numbers is 0, 1 up to 7. Adding 1 to 7, which equal to 1, 0, which equal to 8 in octal. The last one, which is the hexadecimal, the base is 16. The number of valid numerals is 16, which is equal to the base. The set of valid numerals are 0, 1 up to 9, then A, which is equal to 10, B, 11, C, 12, D, 13, E, 14, F, 15. Adding 1 to the highest one, which is F, 15, 1 plus 15, 1 plus F equal 1, 0, which is equal to 16 in decimal. Let's take an example, the number 23 with a subscript of 10. This number means 23 is a decimal number, so we can write it 23 subscript 10, or we can ignore the 10, so it's 23. In both cases, it's a decimal number. So any decimal integer can be expressed exactly in any other integral-based system, and vice versa. For example, if we have the number 243.51 to the base 10 subscript 10, we have the floating point. The integer part is 243. Starting from the 3 is the unit digit, so it's a 3 times 10 to the power 0, starting from the power 0. 4 is the 10th digit, so 4 times 10 to the power 1, 10th digit. We have 2, we multiply 2 to 10 to the power 2, which is the 100th digit. Now to the right side of the decimal point, the fractional part, we have the 5. We multiply 5 to 10 to the power minus 1. 1 we multiply to 10 to the power minus 2. If we do simple addition, the result will be 243.51. Another example, we have this number 10110.01 subscript 2. This means that this number is in binary system. To represent it or to convert it to decimal system, we're starting from the decimal point. From the decimal point to the left side, which is the integer part, we have the 0. 0 is the unit digit. So we multiply 0 to 2 to the power 0 because it's the base 2. And we all the time we start from 0. Next we have 1, the green one. 1 times 2 to the power 1, the 10th digit. Next we have the hundredths digit, which is in purple. So 1 times 2 to the power 2. Next we have the 0 times 2 to the power 3. Next we have the red one times 2 to the power 4. The fractional part, we have 0, 1. 0 times 2 to the power minus 1. We have 1 times 2 to the power minus 2. We have to do simple calculations using calculator. The result will be 22.25 decimal. Now let's learn how to convert from decimal to any base. We have to divide the number into two parts, the integer part and the fractional part. This is the algorithm. Let's take an example to understand it. We need to divide or to convert the number 113 to binary number. So 113 in decimal, we need to convert it to binary. So we divide it by 2. So 113, if we divide it by 2, the answer is 56. The remainder is 1, so 1 is an output. We divide 56 by 2, the result is 28, and the remainder is 0, so the 0 is an output. We divide 28 by 2, the answer is 14, the remainder is 0, so we have 0 as an output. 14 divided by 2, it's 7, remainder is 0 as output. 7 divided by 2, it's a 3, the remainder is 1. Put 1 as output. 3 divided by 2, it's 1, and the remainder is 1. Put it as output. 1 divided by 2, it's 0, and the remainder is output, which is 1. We stop here because we reach to the number 0. The first remainder, which is the least significant bit, and the last one, the last remainder, which is the most significant bit, which is written as 113 equal to 1110001 in binary. Be careful of the order of the number. Remember these two tables. Power of 2, we have 2 to the power minus 2 equal to 0.25, 2 to the power minus 1, 0.5, 2 to the power 0 or any number to the power 0 equal 1, 2 to the power 1, 2, 2 to the power 2, it's 4, each time multiply by 2, 2 times 2, it's 4, 4 times 2, 8, 8 times 2, 16, and so on. We have the decimal number 0 up to 15. If we represent these decimal numbers in binary by 4 digits, 0 represented as 4 zeros, 1 as 0001, 2 as 0010, and so on. The hexadecimal representation of 0 is 0, the hexadecimal representation of 3 is a 3, till the number 9 is 9, but the hexadecimal representation of the decimal number of 10, it's A, 11 is B, 12 C, 13 is D, 14 is E, 15 is F, and the binary or the representation of F and 15 is 1111. Remember these two tables. How to convert the fractional part. Let's take an example. And this is the algorithm. Convert 0.4304 from decimal to number system of base 5. So we have the fractional part 0.4304. We multiply it by 5. The result is 2.1520. We take the integer part, which is the number 2 in red color, as an output. The remainder is 0.1520. Just omit the integer part. Again, multiplied by 5. The result is 0.7600. The integer part is 0. Take it as output. Multiplied by 5. The result is 3.8000. 3 is an output. It's the integer part. The remainder is 0.8 multiplied by 5. The result is 4.0000. 4 is the integer part. Take it as an output. The remainder is 000, so we stop. So the output 0.4304 equal to 0.2034, and be careful of the order. Let's take another example. Convert the number 0.34375 decimal number to binary with 4 bits to the right of the binary point. So we have the fractional part 0.34375. We multiply it by 2 because we want to convert it to binary. So the result is 0.68750. The integer part is 0. We multiplied the fractional part by 2. The result is 1.37500. The integer part is 1. Take it as an output. The remainder is 0.37500 multiplied by 2. The result is 0.75000. Take the 0 as an output. Multiplied by 2. The result is 1.5. Take the 1 as an output. Done, because we reached for the 4 digits as required by the question. Now let's talk about how to convert from any base to decimal. We learned how to convert from decimal to any base. Let's talk about the opposite side, from any base to decimal. To understand how to convert it from any base to decimal, let's take an example. Suppose that we want to convert the binary number 10.11, which is binary number, to decimal equivalent. Simply, starting from the decimal point, we have the 0 in the purple color. We multiply it to 2 to the power 0 all the time. The next one, multiply to 2 to the power 1. To the right side of the binary point, we have the 1 in the purple color. So 1 times 2 to the power minus 1. Then the 1 in the green color times 2 to the power minus 2. After calculations, the result is 2.75 in decimal. Let's take another example. Suppose that we want to convert the hexadecimal number 1A.5 to decimal equivalent. It's 1A.5. A means 10. You have to remember that table. So starting from A, the integer part, times 16 to the power 0. Then 1 times 16 to the power 1. Then 5 times 16 to the power minus 1. After addition and multiplication, the result is 26.3125 in decimal. Now let's talk about converting between bases. I think it's very simple. The intermediate number system is the decimal. So to convert from base x to base y, we have to convert base x to decimal. Then we convert decimal to base y. For example, to convert the number 3124 base 4 to base 3, let's convert it to decimal number. So we have 1 times 4 to the power 0, 2 times 4 to the power 1, 1 times 4 to the power 2. We have 3 times 4 to the power 3. So the result is 217 in decimal. Convert 217 to the base 3. We have to divide. 217 divided by 3 The result is 72, the remainder is 1. 72 divided by 3, it's 24, remainder 0. 24 divided by 3, it's 8, remainder 0. 8 divided by 3, it's 2, remainder 2. 2 divided by 3, the result is 0 and the remainder is 2. So the answer is 31214 and to the base 4 equal to 22001 to the base 3. Be careful to the order of numbers. Binary numbering system is the most important base system for digital computers. But these numbers are too long to be represented, so we use the hexadecimal number system or the octal number system to represent the binary system. So how to convert between power of two bases? Power of two bases are the octal, the hexadecimal, and the binary number systems. We have to know that each octal digit is equivalent to a group of 3 binary digits called octet, and each hexadecimal digit is equivalent to a group of 4 binary digits called hextet. We convert from binary to octal and from binary to hexadecimal by simply grouping bits. So how to convert from binary to octal? Let's take an example. Convert the following number from binary to octal. We have this number in binary. We make a grouping starting from the right hand side. So we have 101 from the right hand side, 110, 010, 011. We have 01, which is 2 digits. We add another 0 to make it 3 digits. So starting from the right side, 101 means 5 in octal, and 011 means 3. 010 equals 2 and 110 equals 6. 010 it's 2. So this number binary equal to 26235 in octal. And we do concatenation. As you can see here, concatenation, it's not addition. How to convert binary to hexadecimal? Let's take an example. The same number in binary, we do grouping but for 4 digits, 4 bits. So we have 1011 from the right hand side, 1001, 0011. We have 01, so we add 2 zeros to the left side. So starting from the right hand side, we have 1101 in hexadecimal equal D, 1001 equal 9, 1100 it's C, and 0010 it's 2. So this number in binary equivalent to 2C9D in hexadecimal. When we do concatenation, it's not addition. So to convert from hexadecimal to octal and from octal to hexadecimal, simply we can convert to binary and from binary to octal and vice versa. And let's consider this one as the end of part 1 of this chapter 2.